Greetings everyone. My name is Itai Chitungo. I'm a junior lecturer at the University of Zimbabwe, Chemical Pathology Unit. Today I'm going to give you an overview of statistics and how we use statistics in the laboratory. The objectives of this talk are going to be looking at statistical measures and their application, especially using the Westgard Rule, to assess instruments, reagents, and control products using various statistical tools, to evaluate lab precision and accuracy, and also to use statistics to choose and recommend control materials based on shelf life, boxing, chemical relevant decision levels, matrix effects, and interlaboratory comparison programs. So what are statistical measures? Most of us knows the widely used statistical measures such as your mean, standard deviation, but there are also coefficient of variance, and there's also standard deviation index, which is used for interlaboratory comparison. What do we use mean for? Mean or average is the laboratory best estimate of analyzed true value for a specific level of control. Standard deviation is a statistic that quantifies how close numerical values are, i.e. when you're looking at quality control values and how they relate to each other. The term precision is often used interchangeably with standard deviation. Another term that is mostly used within laboratory is imprecision or inaccuracy, and this determines how far apart numerical values are from each other. What are the applications of standard deviation? Standard deviation may be used to monitor ongoing day-to-day performance. For instance, if during the next week of testing, the standard deviation calculated in example for normal potassium control increases from 0.08 to 0.16 millimoles, this indicates a serious loss of precision. This instability may be due to malfunction of analytical process. Investigation of the system is necessary, and the following questions should be asked. 1. Has the reagent or reagent lot changed recently? Secondly, has maintenance been performed routinely or scheduled? Does the potassium electrode require cleaning or replacement? Are the reagent and sample pipettes operating correctly? Has the test operator changed recently? All these questions, plus others that I will not mention here, are relevant in order for us to troubleshoot and find where we'll be able to correct for these anomalies. Hence, this all started because the standard deviation had moved or had doubled by 0.8 millimoles. Standard deviation is also useful when you are developing Levy-Jennings charts. It is commonly used for day-to-day quality control runs, and this quality control are created for each test and for each level that we are looking at. So we look at abnormally low, subnormal, normal values, and abnormally high values. And within this, we create a range either depending on quality manuals, that it's either 1 standard deviation, 2 standard deviation, or 3 standard deviation, depending on the rigidity of our measures that we want to determine. An example of a Levy-Jennings plot that has been created, as you can see from the presentation, where we are looking within 2 standard deviation. And any values that goes beyond the 2 standard deviation become point of inquiry or investigation for laboratory output. And anything within those normal ranges is then acceptable. However, we should also be cognizant of issues to do with trend and shift that might be informed by this standard deviation on a Levy-Jennings plot. Hence, the Levy-Jennings becomes instrumental in determining what is a systematic error or random error. So what is a systematic error? Systematic error is evidenced by change in the mean of control values. The change in the mean may be gradual and demonstrated as a trend in control values, or it may be abrupt and demonstrated as a shift in control values. So what do you use systematic errors for? A trend indicates a gradual loss of reliability in test system. The trends are usually subtle. Causes of trend may include deterioration of instrument light source, gradual accumulation of debris in sample or reagent tubing, gradual accumulation of debris on electrode surface, aging of reagent, especially on-board aging. Yes, the reagent might be within its shelf life, but it also has a on-board shelf life. And if then it deteriorates, it affects outcome of results. Gradual deterioration of control materials. Your storage of control materials impact in terms of the results that you get from controls. Gradual deterioration of incubation, chamber temperature. This impact mainly enzymes, as these are temperature sensitive. Gradual deterioration of light filters integrity. As a light filter changes, then it means the quality or their effectiveness or efficacy in allowing light passage becomes compromised, hence impacting on outcomes. And lastly, gradual deterioration of our calibration. So our calibration curve is a defined lifespan, and most of the time calibration should be done either weekly or as per reagent change. However, it can extend beyond the useful time period that it is recommended. Hence, we need to troubleshoot and see whether calibration curve is still relevant for our measurements. Another systematic error that we have highlighted is shift. Shift is a abrupt change in the control mean, and this is a result of changing from the usual mean to a different mean. A shift in QC data represents a sudden and dramatic positive or negative change in test performance. Shifts are caused by sudden failure or change in the light source, change in reagent formulation, change in reagent loads, major instrument maintenance, sudden change in incubation temperature. This also affects enzymes, change in room temperature or humidity, failure in sampling system, failure in reagent dispense system, inaccurate calibration or recalibration, as the case may be. Another error that we encounter in the lab is a random error. Technically, random error is any deviation away from an expected results. For quality control results, any positive or negative deviation away from calculated mean is defined as random error. There is acceptable or expected random error as defined and quantified by standard deviation. So our random errors, that's why we put in one standard deviation or two standard deviation as limits. This is to accommodate the error or inaccuracies inherent within the system. However, a random error is one that exceeds both the negative or positive standard deviation as highlighted in our quality manuals. And this is termed unacceptable or unexpected random error, where the data point exceeds 2 or 3 standard deviation limits. Another statistical measure that we use in the lab is the coefficient of variance. The coefficient of variance, CV, is the ratio of standard deviation to the mean and is expressed as a percentage. The coefficient of variance allows the technologists easier comparison of the overall precision. Application of coefficient of variance. The coefficient of variance can be used when comparing two different methods: inter-instrument performance, interlaboratory QC program comparison, EQA, and proficiency testing. The ideal range for a coefficient of variance should be less than 5%. This is what is acceptable. Anything beyond that becomes a point of investigation or an audit to evaluate what the cause might be. Coefficient of variance can also be extended to what we call a coefficient of variance ratio. Although accuracy of test results is paramount in clinical laboratory, precision is just as important. One way laboratory can determine whether precision or a specific test is acceptable is to compare its precision to that of another laboratory performing the same test on the same instrument using the same reagents. What is termed laboratory peer group. An easy way to make this comparison is to divide the laboratory coefficient of variance by the laboratory peer group coefficients of variance obtained from an interlaboratory comparison report. Therefore, calculating the coefficients of variance rate is equal to laboratory coefficients of variance over peer group coefficients of variance. So what is the application of this? For example, if the coefficient of variance of potassium on a particular instrument is 4%, and the potassium for all laboratories using the same instrument is 4.2%, then the coefficient of variance C ratio is 4 over 4.2, which equates to 0.95. Any ratio less than 1 indicates that precision is better than the peer group. Any score greater than 1 indicates that imprecision is larger. Ratio greater than 1.5 indicate a need to investigate the cause of imprecision, and any ratio of 2 or greater usually indicates need for troubleshooting corrective action. Something in the test system is causing the increased imprecision, and patient test results may not be entirely reliable. Certainly, repeated tests such as glucose or for diabetic patients or prothrombin times for patients taking coumadin will not be reliable when the imprecision is high. Another statistical measure is standard deviation index. The standard deviation index is a peer-based estimate of reliability. If the peer group mean is defined as X group, the standard deviation is defined as S group, and the group laboratory mean is defined as X lab. Therefore, standard deviation index is equal to X lab minus X group divided by S group. The standard deviation target should be 0.0, which indicates a perfect comparison with the peer group. The following guidelines may be used for standard deviation index. A value of 1.25 or less is considered acceptable. 1.25 to 1.49 is considered acceptable to marginal performance. Some investigation of the test system may be required. 1.5 to 1.99 is considered marginal performance, and investigation of the test system is recommended. 2 or greater generally is considered to be unacceptable performance, and remedial action is required. We can use the statistics to select control products. Let's give an example of shelf life. When purchasing a quality control product, it is necessary to know the approximate volume of control to be used each day. For example, general chemistry control products are usually sold in 10 ml vials. Laboratories that use 10 ml or more per day generally are not concerned with stability. But for those laboratories that use a low volume of control, 1 ml per day, or for example, shelf life become an important issue. Your quality control shelf life should match or exceed the laboratory normal usage rate, or money will be wasted. Let me give you an example. A laboratory purchases a quality control product that offers only 5 days stability, when their usage rate would require 10 days to fully use that product. Therefore, they will waste about 50% of the product. Consequently, if the laboratory paid 18 cents per mil for the product, the actual cost based on usage is 36 cents per mil. A better purchase choice would have been a more expensive quality control product of 28 cents per mil that offered a 10-day shelf life stability for all analytes. Another example is box pricing. Box pricing is a misleading quote practice that many laboratories fall into at one time or another. Assume a laboratory is negotiating price with 2 vendors for an expensive quality control product. One vendor offers the product at $8 per mil or $144 per box. Another vendor offers the product at $120 per box without quoting per mil. The first vendor provides 18 mils for $144. The product cost per mil from the second vendor is equal to $10 per mil, or $2 per mil more than the box quoted at $144. Always ask for quality control product costs on a per mil basis and not box prices. You can also apply statistics for clinical relevant decisions. It requires the laboratory to compare relevant clinical values for each test to those provided in the quality control product. For example, the laboratory objectives is to purchase a tri-level, 3-level quality control that will allow the lab to control, evaluate the method care for thyroid stimulating hormone at less than 3 micro-international units per mil. Normal TSH between 3.0 and 10.0 micro-international units per milliliter, and abnormal high TSH at greater than 10 micro-international units per mil. The instrument is linear to 50 micro-international units per mil. A quality control vendor offers an immunoassay control with 3 levels. Level 1, 1.03 to 1.23. Normal level, 7.5 to 9.6. Abnormally high, 27.9 to 34.5. This product meets laboratory diagnostic criteria. It contains 3 distinct levels at the decision limits used by the laboratory and adequately challenge the upper limits of linearity of the instrument. A second vendor offers a tri-level product for a reduced price. Low level 3.0 to 5.0. Normal levels 8 to 10. High abnormal levels 45 to 55 micro-international units per mil. In this case, the cheaper product does not control low TSH because the level is higher than the laboratory decision limit. Furthermore, it does not provide adequate control on the high end of the curve because the level for the high control is too near the instrument linearity limit and may often exceed the limit. The price is lower, but the product provides less or no value. Another application of statistics is Interlaboratory Comparison program. Participants in an interlaboratory quality control comparison program is highly recommended. Without such programs, the laboratory becomes a statistical island and has no means to regularly verify the reliability of its work. One of the easiest methods to assess reliability and imprecision is to compare within laboratory method of means and standard deviation to other laboratory using the same instrument or method, what is termed the peer group. Thank you very much for your attention. If you have any questions, you can email me on ichitungo@medschool.uz.ac.zw.